Module 9 begins this way. It's not time to put your head down, dude. Module 9 begins with... Quick, dive for the desk. Are you taking cover, or were you preparing for the class?
For the what?
Were you taking cover, or just that's your way for preparing for class? Okay. Module 9, first paragraph. The vast majority of chemistry revolves around chemical reactions. To study reactions, we must remember the skills we learned in the last two modules, because we will be using the mole concept, stoichiometry, unit conversions, ionic compound naming, and chemical equation balancing skills in this module. If you have trouble understanding some of this module, you might need to go back and review some of those concepts. Okay. So I wanted to start with the encouragement from the very first paragraph. I know there was some consternation expressed once that we have to remember stuff from the last module for this exam. Yeah, you do. You kind of have to be responsible for pretty much everything we've learned up to this point, but specifically those things of moles, stoichiometry, conversions, ionic naming, and chemical equation balancing. So the last two modules, remember I said last module was when we finally started doing chemistry. Up to that point, we were learning the language of chemistry. So today we're going to start on acid-base chemistry, acid-base reactions. And we've learned three basic types of reactions. They go through that in the book. What are the three basic types of reactions we've covered so far?
Which
Types of reactions?
with like formation, decomposition.
Yep. So
Combustion.
right. So Ray said that there's formation. And formation, remember, is it generally looks like something like an A plus a B plus a C produces ABC. We're forming something. We're taking the elemental components, we're bringing them together to form a molecule or molecules. The second was decomposition. I'm going to write decomp. I reminded you that it's not like biology decomposition that gets all slimy and smelly. It's just taking something, a molecule or molecules, and then decomposing them, which means to break them apart. Break them down into their constituent elements, to their basic building blocks. Combustion. Those old bones aching. Yeah, get too old. I'm, what, 3 times as old as you? It's gonna be a long life, man. There we go. Combustion. So you've got complete combustion. These are two subsets of combustion. And incomplete. So what would complete combustion look like using my ABCs? Actually, it won't. It really won't, will it? Because combustion, complete combustion, is going to react to produce carbon dioxide and water. And it reacts with oxygen. So whatever is on this side has to be some combination of carbons, hydrogens, and oxygens. Now that we know those little symbols, something like that. Right? That's combustion of a carbon, hydrogen, oxygen fuel chain. Incomplete combustion looks amazingly like that, except product of reaction is carbon monoxide, not carbon dioxide. And why was the reason for carbon monoxide? Insufficient oxygen in the space, right? The reaction wants to, in quotes, wants to form carbon dioxide, but there's not enough oxygen to go around. So it falls back to an alternate molecule, carbon monoxide, and forms that instead. One I didn't put up here is combustion of a metal or oxidation. It's rusting, basically. So you've got a combustion of metals, which looks more like burning. Some combustion of metals looks like rusting. One's very violent, very quick. One is very slow and very boring. But they're both metals reacting with oxygen, and combustion is primarily understood to be not burning, but reacting with oxygen. Okay, so these are the three main types we've done so far: formation, decomposition, and combustion. The fourth type of reaction you're going to learn now is acid-base. I'm going to write it on top just for space, but an acid-base reaction. We make some space here for acid-base. You're going to find that in order for an acid to function, we think of an acid, what do we generally think of? When I say, be careful, there's a beaker of acid over there. Why would you be careful of the acid?
Acid.
Okay, because it could burn you. It's caustic, right? If I said, be careful, there's an acid, there's a beaker of base over there.
Beaker.
See, we generally know acids, right? The idea of an acid, but when I say, be careful of the base, it doesn't communicate the same thing, right? Man, did you see that movie? It was horrific. Did you hear that, those crime scene movies, stuff like that, they poured acid all over the body to get rid of it? You say they poured base all over the body to get rid of it. And you're like, base? Okay, remember, we've got to realize that acid-base chemistry, acids need bases in order to have their effects. Acid and base, and we're going to learn about the definitions of them in a minute, but for right now, we're going to look at some of the physical characteristics of acids and bases, or at least discuss those physical characteristics. Much in the same way we said before, we've got metals and nonmetals, that metals have certain characteristics and nonmetals have certain characteristics. For example, Oz. What are some of the characteristics of a metal?
Isn't this something that we went up like forever ago?
Yeah, but we went over it.
When
I'm just saying we went over it forever ago. But that can't be more than a year, so it's not really that long ago, right? When I have a metal, let me give you some hints. Metals are malleable, right? They change shape. So metal, if I have it on an anvil, I hit it with a hammer, a metal is going to reshape. And I can tap it and shape it. That's the next one. But a non-metal, I put it on the anvil, I hit it, it's brittle, it breaks up, right? You mentioned the second one, luster. A metal generally can take a shine and look really nice. Non-metals, not so much. You might get a little bit of a glint on them occasionally, but in general, they don't shine up very well. And the third thing we talked about was electroconductivity. A metal conducts electricity, a non-metal doesn't. Okay? Why does, never mind, we'll get into the whys. That's review, and you already know that. For acids and base, there's some characteristics of them as well. We're going to go ahead and contrast those. So over here, I'm going to put my acid characteristics and base characteristics. Forgive me. You know how I feel about markers that shadow all the time, so let's see if we can do a little bit better. Okay. Characteristics. This is all in your book. Acids and bases. This isn't going to last long either. See if I can get a new marker. Okay. So just like with metals and nonmetals, we're going to learn the characteristics of acids and bases. First one they list in your book here is that acids taste sour. Now they do put a disclaimer in there because it is our litigious society today, Don't, if you have a chemical and you want to know if it's an acid or a base, don't taste it to find out. I'm just saying, okay? It might be an acid or base. Either one of them will mess your tongue up. But at the other side of it, we also shouldn't be that afraid of acids because we actually appreciate acids. It's all in the concentration. It's basically all in the strength. For example, when you take a drink of orange juice, and when you take that orange juice, though it may make you go, like that just a little bit, like pucker up just a bit because it's a little bit sour. It's the acid, it's the citric acid in orange juice that you actually are drinking, that you like. It's a little bit of a burn, right? Carbonic acid. Carbonic acid is in your soda. So you drink that soda and you get that little bit of a burn, which your body communicates as refreshing along with the carbonation that's supposedly refreshing. That's carbonic acid that's burning. That's the stuff that takes soot off of fireplaces that you're putting in your throat in that little burn that you like with the soda. Okay? So just because it's an acid or a base doesn't mean we don't eat it all the time. Matter of fact, high cuisine, fine cuisine, they're very intentional about matching and pairing things to balance their acidity and their base characteristics so that it blends on your palate. You know, something that's hearty, something that's sweet, something that's savory, something, all those things involve considerations for acids and bases. Okay? So we use acids, we eat acids all the time. Anytime you eat something that's got the little sour, and those candies that make you just go, that is, you're basically eating acid. Okay. Now again, your stereotype is acid is stuff that eats away flesh and eats away, you know, metals and things like that. That's a different concentration than what you're eating. This is just a sample of it. But generally speaking, if you're eating something and it is sour, it's because what you're eating is acidic. In contrast, bases are bitter. Now, some people have a hard time between sour and bitter. Basic facial response usually is sour does this, and bitter does this. You know, if you watch a little kid and you give them food, you guys never do this, right? You never give kids food that you know is going to make them physically respond. You don't do that, right? Okay. Anyway, apparently some of you can relate to that, but if that child goes, it's probably sour, and if the child goes like that, it's probably bitter. Okay. Sour and bitter. If it's a sour response, it probably is acidic, and if it has a bitter response, it is probably basic.
What about hot sauce? Does that have like
Hot sauce? that's a completely different chemical thing going on. It's not acid and base. Yeah. Capsaicin. Okay, second thing is about the second thing for acids that they list, and it's not really one-to-one with the bases, is that acids are covalent compounds that conduct electricity. You know there's going to be exceptions, right? There's always exceptions to the rule. And up to this point, when we've said, is a molecule ionic or covalent, one of the ways we've been able to test that is say, let's dissolve it in water and see if it conducts electricity. If it conducts electricity, it's ionic. If it doesn't conduct electricity, it's covalent. Okay, that was a good elemental understanding up until today. Beginning today, you have to add one more caveat. If I mix it in water and it conducts electricity, it is either ionic or it's an acid. Because acids are covalent molecules that conduct. They conduct electricity, and we'll get to why that is very quickly. So acids conduct electricity, but they're covalent molecules. They're not ionic. They're covalent. And we said up to this point, in order for something to conduct electricity, it has to have a free-flowing or free-moving charge. And we've explained that when we take sodium chloride and we mix it up in water, when an ionic compound dissolves, what happens is the water molecules get between the sodiums and the chlorines and separate them. And so you have a positive charged sodium ion and a negatively charged chlorine ion. And because there's charges present, we have electricity that can flow. Acids are covalent, and yet they also conduct electricity. So if you were to receive a question on a quiz or a test that said, there's a substance in a beaker, it conducts electricity, what is it? One of the answers might be ionic, one of the answers might be an acidic, an acid, one of them might be a base, and one of them might be ionic or base, or excuse me, an ionic and or acid, right? You need to choose either ionic, or it could be ionic and it could be an acid, just because it conducts. Keep going on the acid side here. So it's sour, it conducts, and lastly they list that it turns blue litmus red. That's right, blue to red. Litmus paper. I need to get some fresh litmus paper. I checked on what I have and it's expired. It's no good, so I'm going to get some more for us. But litmus paper, litmus is an indicator. You can see on the middle of page 314 it talks about an indicator. That an indicator is a substance that turns one color in the presence of acids and another color in the presence of bases. So litmus is usually, we think of that as a paper, litmus paper. Phenolphthalein is a chemical that we use. Phenolphthalein is also, and I'm going to share something with you that I would not recommend, okay, which is really a bad thing, right? Like, don't do this, but it's really, phenolphthalein is a diuretic, okay? And so phenolphthalein has an effect upon the human body, but it's also an indicator. It's used in chemistry. And that's unfortunate about being in a advanced chemistry track in college. And you go through and you learn all the effects of certain chemicals and how, whether they have a taste or not, so whether or not people know that they're consuming it or not, things like that. So there's stories behind all that. Right now we're just going to deal with litmus. Litmus comes in either blue or red. So it starts with a color. Some litmus is red, some litmus paper is blue. In this case, if you were to take a blue litmus paper and bring it in presence of an acid, the blue would turn red. Not surprisingly, what do you think happens on the other side? Red litmus paper turns blue in the presence of the base. So litmus comes in two colors, blue or red, basically predisposed to change. If I bring red litmus paper in the presence of an acid, it's not going to change. It's going to stay red. But if I bring blue in the presence of an acid, it does turn red. If I bring blue in the presence of a base, nothing happens. But if I bring red in the presence of a base, it turns blue. Do you see any mnemonics here that are helping you memorize, maybe? That bases are bitter. I mean, we could probably come up with a Schoolhouse Rock thing on this, right? Bases are bitter, and bases turn blue. What's the key? The letter B. Base, bitter, blue. What's the middle one going to mess it up? Yeah, bases are slippery. So you got to figure that one into the mnemonic too. Bases are bitter, blue, and slippery. Bitter, blue, and slippery. Acids are sour, turn red, and conduct. I know that conduction and slipperiness don't really parallel one another. They're like opposites. Here it's sour, bitter. They're not truly opposites, but they're both taste. This one here is both about litmus. The middle one's kind of off. This one, acids conduct. Acids, one more time, acids are covalent molecules, right? Covalent molecules that conduct. Over here, bases are slippery. Think of bases. Here's the deal. Bases, for now, I want you to think of soap. Soap is a base. What does the bitter taste like? When's the last time you had your mouth washed out with soap? Now, for some of you, it hasn't been, it's been too long. Okay. But if you've ever had that little taste of soap on your mouth, whether from a parental instruction or, you know, maybe you're just in the shower one day and say, hey, I feel like eating soap.
What?
I've heard stupider things out of this group, okay? For whatever case, let's just try it. Oh, that really hurt. Yeah, let's not do that again. Okay, so bases are bitter. Think of soap. You put soap on your tongue. Does anybody go, ooh, nice Irish scent? And no, it's like, ugh, bitter, slippery. What does it feel like in your hand? You get a little bit of water on it, get some soap on your hand, that slippery feeling from the soap, that is what a base feels like. Think of that. Bases is like the slopes of the soap film on your fingers sliding around. Okay, so they're bitter, they're slippery, and turn litmus blue. Acids are sour, they conduct, and they turn blue litmus red. And an indicator. It's on the middle of the page, blue definition, need to learn it. An indicator is a substance when in the presence of an acid turns one color, in the presence of a base turns the other. Now there are some indicators that are clear and they turn color when they either go acidic or basic. And hopefully this will make more sense to us as we go through the module. But for right now, this is one way of approaching determining whether something is an acid or base. If it tastes sour, it's probably an acid. If it tastes bitter, it's probably a base. If it conducts electricity when dissolved in water, it's either an acid or an ionic compound. Bases are slippery, like soap on your fingers. Acids turn blue, litmus red, and bases turn red, litmus blue. Okay? And I would encourage you to think in terms of the B's, the B's, the B's, and just remember that one because it's soap. This is the oddball out then from that mnemonic that it conducts. All right? Now that's one way of considering whether something is an acid or base through these characteristics. The other way of talking about acids and bases is according to their chemical definition. You know, what is it actually? These are true. And while these are true, there's something chemically happening in the background that describes acids and bases. The definitions for that are a couple pages forward on page 317. Page 317. The chemical definitions. This is how chemists define the substances. That an acid is a molecule that donates protons. Acids donate protons. I might get rid of the S here. They donate. Acids donate protons. So, in case there's some people here struggling with English, you know what donate means? Okay? I know this might seem basic, but so acids donate protons. Acids give protons up. Now, what else do we know we've been talking about in chemistry that tend to donate things, to give things up? Like this whole side of the periodic table, right? All of the metals, what do metals do? They tend to give up what? Electrons. Metals give up electrons to become positive ions. Okay. Nonmetals are electron receivers. You could say that metals donate electrons and nonmetals receive the electrons. They accept the electrons, right? So chlorine, for example, wants to get that one electron. It's willing, if anybody's willing to donate, it's willing to accept. And conversely, you could think of it from the other way. If one is willing to accept, the other one's willing to give it up, right? So there's a relationship between metals and nonmetals. One is trying to donate something to get rid of it. The other one is trying to receive something and will take it. The same kind of relationship between metals and nonmetals that form the ionic bonding relationships also exists between acids and bases, because acids donate protons. What do you think I'm going to say next? Accept. So in the way that metals donate electrons, acids donate protons. And in the way that nonmetals receive electrons or accept the electrons, bases accept the protons. So just like it would be saying when we've got metals and nonmetals together and they form these molecules, they do this, they react in this way because their responses complement one another. You know, if everybody's trying to give away electrons and nobody's willing to receive electrons, guess what? The market value of electrons goes way down. Why? Too much supply, no demand. Okay? But when you've got some people that are looking to buy and some people that are looking to sell, now we have an economy. In chemistry, we've got some things that want to give electrons. We've got other things that want to receive electrons. Now we're having chemical reactions. Oh, a modification of that. Here we've got acids and bases. Acids want to donate protons. Bases want to accept protons. Now we have some kind of reciprocal relationship. Now we've got some chemistry taking place. Okay? So, protons. Where do the protons come from? Well, obviously they come from within the molecules, right? You've got an acid and a base that are there together. We're looking for protons, but here is where one of the keys about what a proton is and how it's described in chemistry. That a proton is a hydrogen ion. A proton is a hydrogen ion. If I said to you, what is a proton? You might have come back before and said, a proton is one of the basic, matter of fact, you know, on a test, short answer, what is a proton? A proton is a fundamental building block of all elements. It's a subnuclear component. It's, you know, different words you could say. When I talk about building up an atom, you would say, what are the components of an atom? And they are protons, neutrons, and electrons. And as far as our course is concerned, that's as far as we go, right? Those three basic building blocks. So protons is one of the basic building blocks. If I said to you, okay, let's say that I want to draw a Bohr model of an element. In case I want to draw a Bohr model of hydrogen. It's the simplest one, right? It's the simplest element that we have. Let's look at the protons, neutrons, and electrons of a hydrogen atom. How many protons are in hydrogen? The number of protons comes from its atomic number, right? That tells us how many protons it has. And its number is 1. And how many electrons does it have? Well, if it's a neutral atom, it's going to have as many negative charges as it has positive charges, meaning that it's going to have 1. How many neutrons does it have? Remember, neutrons is the atomic mass minus the atomic number, right? Atomic mass is 1. Atomic number is 1. 1 minus 1 is 0. Good. 0. Don't take anything for granted anymore, okay? 1 minus 1 is 0. So a hydrogen atom has a proton in the nucleus and 1 electron. This is a Bohr diagram, right? 1 electron in orbit. If we did a quantum mechanical, we've got a 1s1 electron around 1 proton with no neutrons. Now, that's a hydrogen atom. If I say that I want to have a hydrogen ion, what does hydrogen want to do? Well, it wants to fill, right? We said before it wants to fill the S, right? Because it's actually a nonmetal. But if I say I'm making it a positive ion, in order to make this a positive ion, what do I need to do? If right now it's neutral, and I want to make it 1 positive, I need to get rid of the 1 negative, right? There's a 1 negative here. If I get rid of the electron, this is a H plus ion, and all it is a proton. So a single proton flying through space could be seen as 2 ways. It's a lost proton from a multi-proton element, or it's a hydrogen atom that lost its 1 electron. They're both true, right? So think of it this way. As acids donate protons, what they're giving up are going to be my hydrogen ions, my +1 ions. That's what it's giving up. And if bases are accepting protons, what they're accepting is hydrogen ions. They're accepting that 1 proton. So acids are donating, bases are accepting protons. Another way of saying that is acids donate positive hydrogen ions and acids accept hydrogen ions. What does that look like in real life? Well, there is an equation on 317 that uses hydrochloric acid. Here is the thing. HCl aqueous. So we've got hydrochloric acid that's diluted in water. And water. Reacts to produce hydronium. And chlorine. Hydronium here is one of those polyatomic ions that you're going to have to memorize. This wasn't on your list before, was it? H3O. H3O positive. It's a polyatomic ion. What's happening there? We've got hydrogen with chlorine. Actually, let me put it down below the equation here.
Does the phase sign matter a lot with this one?
Pardon?
Does the phase sign matter a lot with this one?
Not a lot, but it's generally going to be liquids and aqueous because they're going to be in mixture with one another. They've got to come into contact with one another. So usually if it's a solid, it's going to be in water, which makes it aqueous. I'm going to do the two-dimensional Lewis's here. Remember we had hydrochloric acid and water reacting to produce. Going to go to hydronium, which looks like this. Again, these are two-dimensional. Notice the octets are complete. You've got 3 hydrogens bonded to an oxygen, 2, 4, 6, 8, and every hydrogen has 2. Okay. And chlorine has picked up the 1 extra electron. That wasn't distracting at all. 1 extra electron, and now has a -1 charge. So everything has its octet full. Let me ask you, if you look at this form, look at the top line here, just of the chemical formulas. If I were to say, look at something on the left and find its corresponding component on the right, look for something that has lost a hydrogen. What do you see that you can kind of see on the left and the right? On the right, it's lacking a hydrogen. Pardon? The chlorine over here used to be hydrochloric acid, but now it's just chlorine. This molecule right here went through a process to get over there, and in that process, it donated a hydrogen to somewhere else. It lost a hydrogen, right? So I would suspect that since this donated a hydrogen, this is my acid, in which we know HCl is called hydrochloric acid. Okay, big hint. If the name acid is in the name of the molecule, it's probably an acid. Okay, so hydrochloric acid is A, a base, B, a covalent molecule that conducts electricity. That would be right, wouldn't it? Okay, so hydrochloric acid is the acid. Now I would suspect, since there's 2 and 2, that we can find the reciprocal relationship in the other one. Is that true? Do we see something here that has gained a hydrogen? We do. You can see the form H2O became H3O, and so we know that in this right here, that, and I'm going to write the acid closer to this side, okay? Because this is the acid, the HCl is the acid, and here, this is the base. Yes, sir. So acids and bases, you can see who's gaining and who's losing protons. Now, the reason why I shifted this from the middle over to this other side is that in the reactant side, the acid and the base, as they connect to that other molecule fragment, okay, HCl connects to the fragment of Cl, this is known as its conjugate base. the conjugate base. So in the reactant side, it's an acid. It becomes the conjugate base. And then the base on this side, guess what it becomes? It's a real complicated template here, paradigm. It becomes the conjugate acid. Conjugate acid. Why is it considered the conjugate acid? Because we're going to learn later that all reactions are reversible. I'll say all, that's pretty strong. Virtually all reactions are reversible, because they go back and forth. So if we're living on this side of the reaction, it's acting as an acid. This acid is creating this, it's participating to create this ion. Oh, guess what? When we go this way, this becomes the acceptor of this to become this. So on this side of the reaction, this molecule acts as the acid. On this side, the remnants of that molecule act as a base to go the other way. So usually we're going to talk about the reactant side. If it donates on the reactant side, it's the acid. If it accepts on the reactant side, it's the base. And whatever it becomes is the conjugate opposite. So the base has its corresponding conjugate acid, the acid, the corresponding conjugate base. As I said, H3O is one you're going to have to memorize, hydronium. It's known as hydronium, also known as heavy water. You may have heard of heavy water. It's used in chemical reactors to control the nuclear reactions. So this is a product that they seek to make, and they have, in nuclear reactors, where the control rods are, to control the whole nuclear reaction. So heavy water. Won't kill you, drink it. Just has an extra proton. Yes, sir.
So how do you know if it donates or accepts?
How do I know if what?
If like the you said the ACL is donating, how do you?
Because what I'm going to do, let me get rid of some of this clutter. This just shows the two-dimensional Lewis's so you can see it. What I'm going to do is, as I look at the two different, let me get rid of all of this, just kind of strip it all away. My basic process is when I see what I do is I try to pair things up with what they become. This morphs into something, and this morphs into something. When I look at this side, and I know it's an acid-base reaction, I'm going to say something lost a hydrogen to become something over here. So what over here lost a hydrogen and became something over here? Right. So you see HCl. Matches with Cl. And for HCl to become Cl, it has to lose a hydrogen. So it donates a proton. It gets rid of a hydrogen, which makes this the acid. And then the other, in this case, just two chemicals here. This here, hopefully you see that reacts, and the result is it gains a hydrogen. It accepts a hydrogen. It accepts that proton. So this is the base. So this acid and this base are going to react with one another because one is a giver and one is a taker. They're taking these things, and they become, H2O becomes H3O when it adds the proton. So it's going to add the proton. Think about it like that. Going from here to here, I'm adding a proton. And going from here to there, I'm subtracting a proton. Okay. I'm donating one. So since I'm donating, I'm the acid. And since I'm receiving, I'm the base. And in the process of giving and receiving, they become these things, which, when they're paired up, are the conjugate opposite. So the acid morphs into the conjugate base, and the base morphs into the conjugate acid. And here's the other thing you need to know about all of this, is water is amphiprotic. We'll get into that more tomorrow. But what that basically means is water can act as both an acid and a base. It's one of the other magic things about water. One of the main things we talked about now is the differences in the freezing point based upon hydrogen bonding, what that does to the density, because hydrogen is actually less dense as a solid than as a liquid, and how that provides for life on this planet. Okay? One of the other things about water is that it acts as an acid or a base, whichever is necessary, which is why it's such an amazing molecule to use for so many things. If the reaction needs a base, water will be a base. If the reaction needs an acid, water is fine being an acid. It can both accept and give up protons as needed to react with the other molecule.